I can say this. Given a rule y prime equals f of ty, in a point which I'll call t sub 0, y sub 0. In the case of the example you did, that was the point 0, 1, right? Okay? We can, if f of ty behaves itself, yeah, use the right word here, construct an approximate solution curve through the points t0, y0. Right? Okay? Using some increment delta t. Okay? Smaller delta t gives a more accurate curve. Okay? In the limit, as our delta t approaches 0, the approximate curve approaches the limiting curve make sense? If in the example we did, and you did for homework, you extended for homework, if you'd use an increment of 0.01, the curve would have more closely resembled the solution curve. Of course, we got the solution because we used an equation we could easily solve, just using what you know from first semester calculus. Okay? If we'd have then gone to an increment of 0.001 or 0.0001, as I said, and we're kind of still being a little vague about the connections here, but the smaller the increment you use, the less the slope changes as you move across that increment. So the less error you have when you assume that you have a straight line. Okay? Okay, so as delta t continues to approach 0, the errors get smaller and the accumulated error gets smaller. And in the limit, you get your curve. And this is, of course, provided that f of ty behaves itself. And we'll talk about that in more detail when we get to and so forth. Right now, we're just trying to lay the foundation, get some idea of what the terrain looks like in differential equations course. Okay, so as long as f of ty behaves itself, the solution curve does exist. Okay, by the solution curve, I mean the solution. And there is just one solution for a given point. So we say that is unique. Okay? Now this is the basis of the existence theorem. It basically says as long as f of ty behaves itself, it's got higher derivatives and so forth, another way f of ty cannot behave itself is by having a vertical asymptote, essentially. Okay, a point where a value of t for which f of ty approaches infinity, and you can't cross a point that acts like that. Okay, well, we'll do much more with that later when we actually test some differential equations for existence of solutions. And solutions can exist on intervals between vertical asymptotes, for example. Okay, but don't want to worry too much about that right now. So we're on solid ground for most simple functions f of ty. Okay. Okay, so we're going to look at some of the tricks we use to get these functions to actually give us solutions we can write out and express algebraically. Okay? And another thing that we want to be aware of f of ty result in differential equations whose solutions cannot be expressed in closed form. If I just pick out any old function f of ty, there exists a solution. We just can't write it down. In a similar way, in a similar manner to the fact that e to the x squared has an antiderivative, but there's no way to write it down. There's no integration technique that will give you the integral of e to the x squared, or e to the negative x squared, let's say. Let's do one to keep it finite, okay? Although we can trick e to the negative x squared into giving us the integral from 0 to infinity. But from 0 to any finite number, we can't do it, okay? So you've seen several examples, and you're hopefully aware of functions that you just, not only do the integration techniques that you know not work, okay? There is no technique that will work to give you an antiderivative, for example. And in a similar way, and that's true for most functions that you write down. And for most functions you write down, you can't solve f of ty functions, you can't solve the differential equation. Okay, well, let's look at some differential equations and identify what f of ty is and start getting an idea how these things might be classified.